Okay, welcome to the Forces in Motion notes review. This is Chapter 5 and Chapter 6. Um, in the textbook, I'm going to start by kind of reviewing some friction stuff. Have some issues with the mic here, so hopefully let's just keep it going. Alright, friction. Force that opposes motion. I mean, if it's going against motion or if it's doing any kind of oppositional work towards two surfaces, then it is classified as friction. Rougher surfaces create more friction. An example here is the sandpaper. In this example, the box is being pushed this way. It doesn't push easily that way because there's friction being caused on the ground. Greater the force creates more friction, as in the brake pads. Brake pads are able to apply a tremendous amount of friction due to hydraulics. There are four main types of friction. You have sliding friction, which is the most common on a day-to-day basis. Two objects rubbing against each other. Example of the match over here. It's had a lot of sliding friction because you have the sandpapery kind of stuff over here, and the match itself is has phosphorus on the end, which has it's very easy to ignite with very minimal friction / heat / kinetic energy, which of course all the same thing. Another good example is putting a book on a flat surface and trying to push it. It'll move easier on smooth surfaces like ice, and it'll move less easily on things like dirt or grass or something like that. Rolling friction resistance occurs when round objects as a ball or tire rolls on a flat surface. Tends to be less friction than sliding friction, which is the reason we use the wheel so effectively, but still does cause friction. If there's two things touching, it causes friction. The wheel's touching the ground, so therefore it's causing friction. Fluid friction, obviously dealing with a fluid, which is a liquid or a gas. The swimmer is impacting or having fluid friction. He's actually using it to his advantage. He's pushing the water back and able to propel himself forward as a result. Another good example is air resistance. Air resistance is, if you ever stick your hand out the car window, you know that's a good example of air resistance. You feel the force pushing back on you. Static friction occurs when two objects aren't moving relative to each other. Book on a desk is a good example. I like this diagram here because the box doesn't want to move. There's a certain point though where a force greater than the static friction will overcome that force, being gravity. Not always that force, could be another force. Speaking of forces, let's talk about a major one that plays in your life, and that is gravity. Newton, I say discovered, invented, I don't know, he obviously didn't invent it, but he's the one that kind of realized that there's this attractive force that was applying to the moon and to the apples on the tree, and he concluded that it was universal because it attracted everything in the universe, obviously. A couple of rules of gravity. Gravitational force increases as mass increases. The more mass it has, the more gravity it has. The sun has a tremendous amount of mass, and therefore it's got a lot of gravity. If you remember the Family Guy video from class, they're trying to convince Peter that he is large, and their proof is to show that he has a gravitational orbit because he has such a large mass. So, um, gravitational force decreases as distance increases. So basically means the further you are away from a large gravitational force, the weaker it is. Evidence of this: orbital velocity of the planets. Mercury orbits very fast because it's close to the sun. Pluto not so much because it's very far away. You can also consult that. The gravity FET simulation, which is in the gravity folder of Edmodo. Inverse square law of gravity is it's basic. Mathematically we don't really need to get into it, but what you really need to know is as distance increases, the gravity decreases. It can actually be calculated. So for like every 3 times you move away from a gravitationally strong object like the sun, for 3 times the distance, it gets 9 times weaker. So that's hence the inverse square. 3 squared is 9. 5 squared is 25. So if I move 5 times away from the sun, then my gravity doesn't become 5 times weaker, it becomes 25 times weaker. So what you really should realize is it never comes to 0. That's a very key thing. That's kind of confusing to a lot of people. There's never a place in outer space where you'll be completely gravityless, and therefore you can never be weightless. Which is an interesting thing. We always say the astronauts are weightless, but they really aren't. I'm going to skip past this. I'm going to skip past this and get to the third rule of gravity. It pulls from all sides the same rate. It's one of the reasons that, well, not one of the reasons, it is the reason planets and stars are round. I think that's a very interesting thing. Planets and stars are spheres because gravity pulls inward toward the center of them, because they have the most gravitational influence. I said it's also why people don't fall off the bottom of the planet. This picture is kind of comical because it looks like he's about to fall off the planet because he's in Australia, which is the southern hemisphere, and haha, he's about to fall off. Talk about weight versus mass. They're different. They are related, but they are different. Weight's a measure of gravitational force. Mass, on the other hand, is the amount of matter in an object. If you go to the moon, you're still going to be made of the same number of atoms. It's the easiest way to think about it. What does change is gravity. Weight is equal to mass times gravity. It's oftentimes just referred to as W equals mg, which is weight equals mass times gravity. So when you change planets, you go to another planet, then your weight will change because the gravity is different. But your mass doesn't change. You're still made of the same number of atoms. Very confusing thing. Mass and weight oftentimes referred to as the same thing. They're not. Mass is literally how many... it's easiest to think about the matter that you're made of. And I always say number of atoms. It just makes it easier to remember. Acceleration due to gravity can be calculated. Rate of 9.8 meters a second per second. And instead of saying meters per second, we say meters per second squared. Over here you can see the young lad dropping the ball or the rock or whatever it is. And every second, if you look at the time interval, every second that passes, it accelerates another 9.8 meters a second. This is not exactly 100% mathematically correct because you have things like air resistance that would slow it down, and oppositional force due to gravity. Speaking of, it is oppositional force. It is friction thereby because it opposes gravity, which is a force. And air resistance is an upward force caused by the pressure of air molecules building up on something. When an object reaches terminal velocity, though, acceleration due to gravity stops. It does not accelerate anymore. What happens is it starts falling at a constant rate or a constant speed. Does not mean that it stopped. It simply means it's not accelerating anymore. If you think back to the young lad here with the rock, right? Keeps getting faster and faster and faster, right? When you reach terminal velocity, it stops getting faster and faster and faster. Still falling. It's just not accelerating. Definition of accelerating is change of speed over time, which means is it changing its speed over time, or is it staying at a constant speed? Free fall occurs when gravity is pulling an object, no other force like air is opposing the gravitational force. It's really only truly achieved in space where there's no air, because otherwise there is air. You know, even at the top of a mountain or something, there may be less air, but there's still air. Demonstrated here, the astronauts dropping the feather and the hammer, they fall at the same rate. Take air resistance out, a feather falls the exact same rate. All objects do. Orbits are a combination of two motions, forward motion and a pull of gravity. I think this is best demonstrated with a diagram here. Newton gets the idea from about gravity because the moon, he says the moon is falling. He said the moon should be shooting off in this direction here, but it doesn't for some reason. Why? Because it's being pulled by the force of gravity to Earth. But alternatively, it already has this inertia, or this force that wants to make it go this way. When it wants to go this way and gravity pulls it this way, the result is a circle. That's just another diagram again showing that pulls here, wants to go this way. Imagine if the sun disappeared suddenly, boom, this force is gone. What happens is this force over here overtakes, and as a result, the Earth or the planet or whatever would go flying off in this direction. Last couple things, projectile motion. Horizontal motion, motion that's parallel to the ground. I said here, if gravity's taken out of the question, the object would continue to keep moving forever. However, if you fired a bullet into space, you know, it keeps moving forever because you have no gravity strong enough to impact it. But on Earth, we have gravity. The baseball pitcher's pitch will not keep going forever. It will either hit the ground or hit somebody or hit something. The water's the same way. It doesn't continue to shoot out forever, and instead is pulled down by gravity, because projectile motion is, you know, motion of anything moving through the air, while anything moving through the air moves both horizontally and vertically. Vertical motion is perpendicular to the ground. What does that mean? Well, it's, you know, perpendicular from math. It's basically a big plus sign. When things are shot out and as a projectile horizontally, they fall at the same rate as if you just drop something. It does not matter if it shoots out or if it just dropped. They fall at the exact same rate. That rate being 9.8 meters a second squared. So the guy from the video, if you remember in class, he shoots the two little BB kind of things, and they hit the same exact time. And he uses the famous quote, "Gravity doesn't take a vacation." I don't think it's a famous quote, but I like it. Gravity doesn't take a vacation just because you shoot it out. As it shoots, it still falls at the same rate. Gravity's still pulling exactly 9.8. So projectiles will, instead of going straight like this, they will instead curve and hit the ground, just like any other object that falls, because gravity always pulls that exact same rate. So, alright, well, hope you enjoyed the review, and hopefully I will catch up with you in class.